Hello everyone, I'm Amanda Wolf, welcoming you back to our series of tutorials for machine learning with AMPL. This is tutorial 5 for hyperparameter optimization. Let's review this concept and then break down the code step by step to see how AMPL helps us optimize our cheminformatics models. To start our conversation, let's clarify, what are hyperparameters? Hyperparameters are like your independent variables in an experiment. Your model learns regular parameters from the data during training, but hyperparameters are set by you before the training process actually begins, because they control how the model actually learns and finds those regular parameters in the first place. Consequently, they significantly impact model performance. It's like this. Regular parameters includes the weights and biases that connect the neurons of a neural network learned by backpropagation. But one hyperparameter is the learning rate. This choice dictates how quickly or slowly those regular parameters actually adjust. Hyperparameters also include the number of layers, or the depth of a neural network and its capacity to learn complex patterns, and batch size, or how many training samples are processed at a time, impacting speed and stability. As you can see, finding the best hyperparameters involves creating models, and creating models automatically involves finding the best internal parameters. A very important example of a hyperparameter is the number of random trees in a random forest. A random tree is a decision tree that introduces randomness during construction by selecting a random subset of data and features at each node, training each tree on these different subsets, and ensuring diversity among trees. This randomness reduces overfitting and improves the random forest model's generalization. The final prediction aggregates individual tree outputs, using the majority vote for classification and average for regression, smoothing out noisy or overly specific predictions. Using fewer trees in a model is generally faster, but risks higher variance and underfitting. More trees reduce variance and make the model more stable, but at the cost of increased computational requirements. AMPL offers a variety of hyperparameter optimization methods, including random sampling, grid search, and Bayesian optimization. You can find all of those on the ATOMScience GitHub page. In this tutorial, we will perform a hyperparameter search for a random forest using Bayesian optimization, which is essentially a probabilistic model-based optimization algorithm. Let's take a look at the code. Our first step is setting up directories. Before optimizing anything, we'll set up directories to store the dataset, the trained models, and results. As we iterate through hyperparameter combinations, results can pile up fast. Separating the best models from the rest helps streamline analysis later. So let's examine the code for this step. Firstly, we tell it to ignore warnings about runtime. Then, we establish some important variables for directory setup. Dataset_key specifies the path to our dataset so that we can access it. This directs to the curated dataset slc6a3ki-curated.csv from earlier. Descriptor_type defines the features to use during optimization. Model_dir is the directory where all trained models are stored, and bestModelDir is the directory that keeps and stores only the best performing model. Split_uuid is the pre-saved split UUID from tutorial 2, where we discuss splitting data. We'll need it here. Lastly, we check the OS pathways to store the directories. If they aren't there, the code makes them. So let's run it and make our directories. Our second step is building a parameter dictionary. Now, we define what to optimize and how using a parameter dictionary. This dictionary tells AMPL which model we're working with, what ranges to explore for each hyperparameter, and where to save results. Let's take a look at each component of this code. Hyperparam true signals that we're performing a hyperparameter search instead of training a singular model. Previously featureized true tells AMPL to search for previously generated features instead of regenerating them on the fly. We won't use this one immediately, but it will be useful when exploring other parameter sets at the end. Then we have search_type hyperopt, which specifies the hyperparameter search method. Other options include grid, random, and geometric. Specifications for each hyperparameter search method is different, explained in the full documentation. But here, we are using the Bayesian optimization method. Model type RF10 instructs AMPL to train 10 random forest models with different settings. It could be set much higher. RFE, uniform int, 8,512, optimizes the number of estimators, or trees, in the random forest between 8 and 512. Similarly, RFD and RFF define ranges for tree depth and number of features used. Result_dir specifies directories for saving all models, and also the best performing models. Real quick, let's run the code and get those parameters initialized. Our third step is to run the search. Remember back to tutorial 3 when we trained one model? Now we execute the hyperparameter optimization using AMPL's hyperparam search wrapper. This module simplifies the process of training and evaluating multiple models at a time. Looking over each function, hyperparam search wrapper is what we just mentioned, and it handles running multiple models for us. Parse_params converts our parameter dictionary into an AMPL readable format. Then build_search sets up the optimization process by generating a list of parameter combinations to evaluate. Run_search executes the search, training models with different hyperparameter combinations and evaluating their performance. The output from hs.run_search will represent the progress and results of the hyperparameter search for the random forest model. Let's see it. Send the code. Okay, we've got a lot of information here. Let's make this digestible. Each one of these main trial blocks corresponds to a single random forest model trained with a unique combination of hyperparameters. See this first line? It's like our map legend. It explains the corresponding types of important results that you can see for each model to understand each block. Let's use the second block as an example. The key hyperparameters in the legend include RF_estimators, which is the number of trees in the random forest, RF_max_depth, which is the maximum depth of each tree, RF max feature, which is the maximum number of features considered for splits. And for this trial, the RF estimators are 233, the RF max depth is 28, and the RF max feature is 12. Other performance metrics to know include train R2 and train RMS, which measure the model's fit on the training data. R² indicates how well the model explains the variance in the data, and RMS, root mean square error, represents the average prediction error. Valid R2 and valid MRS are also there. They measure the model's performance on the validation dataset used to evaluate the model's generalization. Test R2 and test RMS are there too, and they measure, as you can guess, the model's performance on the test dataset, which represents how well it performs on unseen data. We can see that train R2 equals 0.948, valid R2 equals 0.481, and test R2 equals 0.944, indicating how well the model fits the different data subsets. We look at model parameters. The combination of hyperparameters values used for that trial is shown in this format here. Then we see the progress and best loss. The progress bar here shows how far along the search is. This block is trial 1 of 10 with 10% of the trials completed, and best loss displays the lowest loss or error achieved so far during the search. Then the model file paths. Each trained model is saved as a tarball file in the specified directory. The file path allows you to revisit or analyze a specific model later. The best model will be saved in this path here, along with a CSV file containing regression performance for all trained models. All of the models are saved in this path here. These models can be explored using the functions that we're just about to get to. Our last step is to analyze the models. Here's the key code. Import atomsci.ddm.pipeline.compare models just imports the module to compare and find the best model for us. Get file system perf results reads the results from model dir. It gathers performance metrics for all the trained models. Then sort values sorts here by the validation R² score. R² reflects how well a model generalizes to unseen data, so we sort by this to identify the top performing models. Head simply extracts and displays key metrics for the best models, and this includes model UUID, which is a unique identifier for each model, model parameters dict, which is the exact hyperparameter settings, and best valid R2 score, which is the model's validation performance, and best test R2 score, which is its performance on the test set. Let's run it. You see our results pop up, nicely sorted by performance. And that's that. These insights are invaluable for refining future experiments. A more comprehensive analysis of the hyperparameter performance is explored in the next tutorial, Tutorial 6. Here, we only have some bonus content left about different model types if you're interested. It'll be important for future tutorials when we compare these different varieties of models. Briefly, let's talk about going beyond random forests. AMPL isn't limited to them, so let's look at alternatives. The parameters used for these other types are used in just the same ways as earlier with the parameter dictionary segment. For neural networks, you can use these parameters here. LR controls the learning rate. Log uniform -13.8, -3 means the logarithm of the learning rate is uniformly distributed between -13.8 and -3. LS controls layer sizes. 3, 8, 512 means 3 layers with sizes ranging between 8 and 512 neurons. A good strategy is to start with fewer layers and slowly increase the number until performance plateaus. DP controls dropout. 3, 0, 0.4 means 3 dropout layers with a probability of zeroing a weight between 0 and 40%. This needs to match the number of layers specified with LS and should range between 0 and 50%. Then, max epochs controls how long to train each model. Training for more epochs increases runtime, but allows models more time to optimize. XGBoost models are also available. You can use these parameters for them. XGBG stands for XGB gamma and controls the minimum loss reduction required to make a further partition on a leaf node of the tree. XGBL stands for XGB learning rate and controls the boosting learning rate searching domain of XGBoost models. You can train an XGBoost model with a fingerprint split too, with these adjustments. A fingerprint splitter provides a more stringent test of model performance by making sure the validation and test compounds are structurally dissimilar to the training set compounds. The fingerprint split UUID is provided with the dataset files. Finally, you can use an XGBoost model with a scaffold split and ECFP fingerprints, which is a novel class of topological fingerprints for molecular characterization, which for us may be very useful. These are the new lines of code for ECFP fingerprint models, and that's all for our bonus content. So that's how we perform hyperparameter optimization with AMPL. By systematically tuning hyperparameters, we unlock the full potential of our machine learning models. Next time, we'll compare these models in depth to select the best one for production. We'll see you in Tutorial 6. Thank you.